Imagine having the master key to your own house, walking right up to the front door and, realizing the lock has just been completely overridden by a satellite in orbit.
Yeah, it doesn't matter if your name is on the deed, honestly.
Exactly. It doesn't matter that you have the physical key right there in your hand. The lock just refuses to turn because, well, a centralized command structure in the cloud decided you aren't trusted anymore.
Right, which is wild to think about.
It is. And today, that's exactly what we're looking at. We're diving into how modern cybersecurity software defends itself against basically everyone, including you.
Yeah, we've got a really massive stack of confidential sources for this deep dive.
We really do. We're talking certified administrator guides, master troubleshooting checklists, internal training manuals for CrowdStrike Falcon.
Which, just for context, is one of the most widely deployed security platforms on the planet right now.
Right. So our mission today is to just pull back the curtain on how elite enterprise security actually works in practice, like the microscopic, highly technical details.
Because it's not just about clicking install. We're looking at how these invisible guards get deployed across, tens of thousands of machines.
How they literally fight with your own corporate network, what happens when they go offline, and how they completely lock down your hardware.
It's a total fundamental shift in how we think about computer architecture.
How so? I mean, what was the old way of thinking?
Well, for decades, the assumption was just if you own the hardware, you control the software. End of story.
Right, like my computer, my rules.
Exactly. But when we look at these administrator guides, we're seeing a completely different philosophy. We're examining the architecture of cloud-resilient defense here.
And the difference between a successful invisible deployment and a completely compromised corporate network, it almost always comes down to the precise implementation of the mechanisms we're about to unpack.
Yeah, and honestly, if you are listening to this deep dive on a corporate laptop right now, there is a very, very good chance that an invisible sensor is currently running deep inside your operating system.
Silently monitoring the media player you're using to stream this audio and phoning home to a cloud server.
Yep, it's already there.
So let's figure out how it actually got there. Because before a single line of code can start protecting a machine, it has to know, well, who it's working for.
Right, it needs a routing identifier.
And according to the deployment manuals, that brings us to the absolute foundational element of any installation, the customer ID.
Or the CID, as you'll see it constantly referred to in the documentation.
The CID, okay.
Yeah, and you literally cannot install a sensor without this. Like, if you just download the installer executable and try to run it on a machine without a CID, the software simply fails to initialize.
It just flat out rejects it.
Completely. It is the absolute non-negotiable prerequisite that links a single piece of endpoint hardware back to a highly specific, isolated Falcon tenant in the cloud.
Okay, so the manual specifies that the CID is a 32-character hexadecimal string. Let's break that down for a second, because we see hexadecimal used everywhere in computing, right? We aren't just talking about a random password here.
No, not at all. Hexadecimal is a base 16 number system.
Okay, meaning what?
Well, our normal counting system is base 10, right? 0 through 9. Hexadecimal uses 0 through 9, and then it uses the letters A through F to represent values 10 through 15.
Oh, right. So that's why you see all those letters mixed in.
Exactly. And the reason systems use a 32-character hexadecimal string is because it allows for just a massive cryptographic space. It's essentially a universally unique identifier, or a UID.
So when your organization buys the software and your cloud environment gets spun up, some mathematical algorithm just generates this specific 32-character string.
Yep. And the sheer number of possible combinations, I mean, we're talking 16 to the power of 32, it guarantees that no two companies on Earth will ever accidentally generate the same CID.
Okay, so it's essentially the cryptographic license plate for the organization.
That's a great way to put it.
So if I'm the IT administrator tasked with rolling this out to my entire company, where do I actually find this license plate?
You have to log into the main administrative console in your web browser. Then you navigate to a specific section called Host Setup and Management.
Okay.
And then you dig down into a subsection called Sensor Downloads. The CID is displayed right there at the top of the page.
Host Setup and Management, sensor downloads. Got it.
And is it just like a static string?
Yeah, it's static. It doesn't change day to day.
Okay, well, here is where we need to look at the real-world operational security of this. Because we have this 32-character string. It's static. It's the core routing identifier.
Right.
What happens if, say, a developer at the company is writing a script to automate the installation, and they post a snippet of their code on Stack Overflow asking for help.
Oh, I see where you're going with this.
Yeah, like they forget to scrub the CID out of the code. Can anyone, anywhere on the internet, just take that string and use it to install a sensor that connects to my corporate cloud? Out of the box. By default. Yes.
Wait, really?
Yes. And that is a significant architectural vulnerability that admins have to understand. If someone possesses your CID, they have a technical ability to deploy a sensor that will successfully register with your specific cloud tenant.
But wait, why is that actually a problem? I mean, if some random person on the internet installs CrowdStrike on their personal computer using my CID, isn't that just giving them free antivirus on my dime?
I mean, sure.
Like, it seems like I'm losing money on licensing, but it doesn't really sound like a security breach.
Well, let's take that a step further and look at how a threat actor could actually weaponize that.
Okay.
Imagine an attacker spins up 10,000 virtual machines in an Amazon Web Services data center.
Wow. Okay. 10,000.
Right. And they install a sensor on all 10,000 machines using your leaked CID. Suddenly, your cloud console is just flooded.
Oh, man. Your administrative dashboard is just overwhelmed with 10,000 new hosts.
Exactly. But it gets more dangerous. The attacker could start intentionally detonating malware on those virtual machines.
Oh, I see. They aren't trying to hack my network directly. They're using the leaked CID to execute a denial of service attack against my security operations center.
Precisely. They create this massive smokescreen. Your security team is suddenly getting bombarded with thousands of critical alerts a minute from these fake machines.
And while your team is scrambling to figure out what is happening, the attacker launches their real targeted attack against your actual corporate infrastructure.
Knowing full well your defenders are completely blinded by the noise.
That is terrifying.
It is. Furthermore, in highly regulated industries like finance or healthcare, you need mathematically verifiable controls over exactly what hardware is authorized to connect to your environment.
Right. A static string that can just be copied and pasted off a forum doesn't really meet that standard.
No, it doesn't.
So we have a serious problem here. The deployment mechanism relies on a static key, but the real world absolutely requires dynamic control. How do the administrator guides tell us to solve this?
The solution is a feature called installation tokens.
Installation tokens.
Okay. Yeah, you have to explicitly enable this in the Cloud Console. Once an administrator toggles this feature on, the security model of the deployment fundamentally shifts.
How so?
Because simply having the static CID is no longer sufficient. An installer now needs both the CID and a dynamic, valid, unexpired installation token to successfully force the software to connect to the cloud.
Got it. So it basically turns a single-factor authentication process into two-factor authentication for software deployment.
That's exactly it.
You need the permanent organizational identifier, the CID, and you need a temporary authorized passcode, the token.
Right. And you have very granular control over those passcodes. When you generate an installation token, the cloud platform asks you to define its lifespan.
Like how long it's good for.
Exactly. You can set it to expire after a year, which you might use if you're utilizing an automated software management tool that just slowly deploys software to new laptops as they're purchased.
Okay, that makes sense.
Or you can set it for 90 days. You can even set it for a very tight 30-day window if, say, you're bringing in an external IT contractor to help provision a new office.
Okay, let me push back on the mechanics of that lifespan for a second, because this seems like it could create a massive headache for an IT team.
What do you mean?
Well, let's say I hire that contractor. I give them a 30-day token. They spend 2 weeks installing the sensor on 500 laptops.
Okay.
But on day 15, we catch the contractor violating a security policy, and we terminate their contract immediately. I log into the Cloud Console, and I manually revoke their installation token to ensure they can't deploy any more machines.
Right. Good standard procedure.
But if that token is the required passport for the sensor to exist, what happens to the 500 laptops that were already deployed using that now revoked token? Do those sensors suddenly just drop offline?
Oh, I see your concern. The mechanics of that handoff are actually quite elegant. The sensors on those 500 laptops do not break, and they do not go offline.
Wait, why not? If the token is invalid, shouldn't the sensor be invalid?
Because the installation token is strictly an onboarding pass. It's not a permanent passport.
Oh, I think I get it.
Yeah, the token is only validated by the cloud at the precise millisecond of installation. Once the software is successfully installed, it reaches out to the cloud, authenticates with the CID and the token, and the cloud says, "Okay, you are authorized."
And then what?
At that point, the cloud provisions a brand new, unique agent ID specifically for that single piece of hardware. From that moment forward, the sensor uses its unique agent ID to communicate.
So it just completely discards and forgets the installation token.
Exactly. It no longer needs it.
Wow, that solves a massive operational risk.
Because they transition to using their unique agent IDs. You maintain total access control over the perimeter without risking self-sabotage.
Okay, so we have the deployment identity lockdown. We have our CID, and we have our time-limited tokens. Now we face the actual logistical reality of enterprise IT.
Right, the fun part.
Because if you have a company with 10,000 employees spread across 12 time zones, you absolutely cannot ask 10,000 people to double-click an installer file and follow a setup wizard.
Oh, absolutely not. The help desk would instantly collapse under the weight of people calling in because they clicked the wrong button.
Scale really changes everything. You cannot rely on user interaction. The entire process must be automated, and more importantly, it must be completely invisible to the end user.
Yeah, the employees shouldn't even know it's happening.
The sources refer to this as silent command line deployment. How do administrators actually execute this across an entire company?
They use centralized deployment orchestration systems. On Windows environments, this is typically Microsoft Endpoint Configuration Manager, formerly known as SCCM, or cloud-based tools like Microsoft Intune.
Okay, so they write a script, load it into Intune, and Intune just pushes that script down to the 10,000 laptops in the background?
Exactly. The script executes the installer using specific command line flags.
Let's analyze the exact execution string for a Windows machine. If I'm writing that script, what am I typing to make this happen invisibly?
You are calling the executable, which is windowsensor.exe, but the critical part is the arguments you pass to it.
Okay, lay it on me.
The standard enterprise deployment string is windowsensor.exe space forward slash install space forward slash quiet space forward slash nor start space CID equals your CID.
Okay, so windowsensor.exe, install quiet nor start CID. Your CID. Let's unpack those arguments. Install tells the executable what action to take.
Right.
Quiet is the command that tells the Windows installer framework to suppress all graphical user interfaces.
Yep. The user sees no loading bar, no pop-ups, no terms and conditions to accept. It's just a ghost process running in the background.
But I want to focus on that third flag, nor start.
Ah, yes, the superpower.
Seriously, because usually when I install something that embeds itself deep into my operating system, especially security software that needs to monitor the kernel, track network packets, and watch every single file execution, my computer throws a fit.
It demands a reboot.
Always. It pops up a massive warning saying, your PC must restart to complete installation, and usually gives me a countdown timer. Are the manuals really saying you can inject a kernel-level security sensor into 10,000 live machines without a single person having to reboot?
That is exactly what the architecture allows, and honestly, it represents a massive evolutionary leap from legacy antivirus software.
How does it even do that?
Well, to understand why this is such a superpower, we have to look at how operating systems actually load drivers into memory.
Okay, walk me through the old way first.
Yeah.
Why did legacy antivirus require a reboot?
So operating systems are basically divided into two main areas, user space and kernel space. User space is where your web browser and word processor run. If a user space application crashes, the program closes, but your computer just keeps running.
Right. Annoying, but not fatal.
Exactly. But the kernel space is the absolute core of the operating system. It manages the hardware, the memory, the CPU. If something crashes in the kernel, you get the blue screen of death, and the whole computer goes down.
So security software needs to live in the kernel to be effective.
Right. And legacy antivirus products relied heavily on injecting heavy, clunky drivers directly into the kernel space to intercept file operations.
Okay.
Because the kernel is so highly protected, you generally couldn't just shove a massive driver into it while the system was actively processing thousands of threads. The antivirus installer had to stage the files, flag the operating system registry, and demand a reboot.
So when the computer restarted, the OS bootloader would load the antivirus drivers into the kernel before it loaded the rest of the operating system.
Yes. It was essentially building the operating system around the security software during the boot sequence, which of course meant interrupting whatever the user was doing.
Okay, so how does modern software get around that?
Modern lightweight sensors use a completely different approach. They leverage modern operating system APIs. For example, on Windows, the Falcon sensor hooks into a system called Event Tracing for Windows, or ETW.
Event tracing for Windows. Okay.
It's a built-in telemetry system that Windows already runs. The sensor doesn't need to jam a heavy driver deep into the core kernel and wait for a reboot to intercept raw disk I/O.
What does it do instead?
It dynamically registers itself with the ETW system and basically says, hey, Windows, please forward me a copy of every process creation event and network connection event as they happen.
Ah, so it acts more like a high-speed subscriber to the operating system's existing newsfeed rather than trying to physically rewire the printing press.
That is a brilliant way to put it, yeah. Because it's subscribing to an existing framework via dynamic linking, it can be injected into a live running operating system.
So an employee could be rendering a massive 3D video file.
And the silent installation script runs in the background. The sensor installs, registers its dynamic drivers, authenticates with the cloud, and begins applying prevention policies instantly without the user ever noticing a blip in their rendering software.
The operational cost savings of not forcing 10,000 employees to stop working for 10 minutes to reboot their machines, I mean, that's immense.
It really is.
What about the engineers on Macs or the developers running Linux servers? Is the deployment script exactly the same?
The philosophy of silent deployment is the same, but the underlying OS architecture dictates different tooling. On macOS and Linux, you rely on a specific command line utility called Falcon cast to Falcon control.
Falcon Cal, got it.
You deploy the base package, a .pkg file on Mac, or a .rpm or .deb file on Linux Dash, and then your script runs a Falcon cackle command to inject the CID in the token.
Now, I know Apple has spent the last decade locking down macOS in the name of user privacy. Does Apple just happily let a silent deployment script install a system-wide security sensor without complaining?
Not a chance.
I didn't think so.
No, macOS introduces a highly critical friction point that enterprise administrators have to navigate really carefully. Apple utilizes a security framework called System Integrity Protection.
Right.
And they have strict privacy controls that require explicit user consent for any application to access certain parts of the hard drive or monitor system events.
So even if your script installs the software perfectly.
If the macOS operating system hasn't explicitly granted the sensor something called full disk access, the sensor is effectively blind. It won't be able to scan protected directories, monitor network extensions, or stop a threat.
What happens on the user's end?
By default, macOS will immediately throw a pop-up window on the user's screen, asking them to manually open their system settings, navigate to the Privacy tab, authenticate with their fingerprint, and toggle a switch to allow the software to run.
Which completely destroys the concept of a silent, automated deployment.
Oh, completely.
If you rely on 10,000 users to manually navigate Apple's system settings, half of them will just click cancel because they think it's a virus, and the other half will literally just forget to do it. You're going to have a massive fleet of unprotected machines.
Exactly. Which is why deploying to Macs at scale absolutely mandates the use of an MDM, a mobile device management tool, like Jamf Pro or Microsoft Intune for Mac.
Okay, how does the MDM solve it?
Before the IT team even thinks about pushing the sensor installation package, they use the MDM to push down a specific XML configuration profile to all the Macs.
Okay.
This profile is cryptographically signed by the MDM, which the Mac already trusts. The profile explicitly tells the macOS operating system when an application from the developer CrowdStrike tries to install system extensions and asks for full disk access, you're to grant those permissions automatically, completely silently, without prompting the user.
It's like pre-clearing a diplomat before they arrive at the border. You use the MDM to file the paperwork in advance, so when the silent Falcon Stubble installation script finally runs, the software just walks straight through customs without being stopped, questioned, or triggering any alarms.
That is exactly how it works. Now, there is one more granular troubleshooting detail regarding these automated scripts that the documentation really highlights. It involves something called the provisioning window.
The provisioning window, what is that?
Well, when you run that silent install command, the local installer process doesn't instantly consider itself finished just because it copied the files to the hard drive.
Oh, it doesn't?
No, it attempts to verify that the installation was actually successful. To do that, it waits in the background while the newly installed sensor reaches out to the CrowdStrike cloud, authenticates using its CID and token, and successfully downloads its initial set of prevention policies.
Okay, that sounds reasonable.
But by default, the installer process will hang there, waiting for up to 20 minutes for this cloud communication to succeed before it reports back to your deployment software.
20 minutes. If the software installs in seconds, why does it wait 20 minutes to confirm?
It's a buffer designed to handle terrible network conditions. You might be deploying to a laptop in a hotel with a really slow Wi-Fi captive portal, or a server connected via a high-latency satellite link. The installer just gives the sensor a generous window to establish that critical first connection.
Yeah, but if you're an IT administrator pushing a script to 5,000 machines, you might not want your deployment tool to freeze and hang for 20 minutes on every single machine if there happens to be a firewall issue blocking the traffic.
Right, you want a script to fail fast, or just finish the local installation and move on to the next task.
So is there a way to bypass that waiting period in the script?
Yes, the documentation provides a specific command line argument for this. Prov no wait 1.
Prov no wait 1. Provisioning no wait.
Exactly. If you append that to your execution string, the installer copies the files, starts the local service, and immediately exits, reporting a success code back to your deployment tool in seconds.
Oh, nice.
The sensor will still aggressively try to connect to the cloud in the background, but your deployment script doesn't have to wait around to babysit the process. It's a vital flag for optimizing massive rollouts.
Okay, so we've solved the problem of getting the sensor onto 10,000 machines silently. The scripts ran, the OS didn't require a reboot, the Mac MDM profiles cleared the way, and the software is sitting on the hard drive.
Job done.
But not quite, because a sensor sitting silently on a hard drive is just a dormant piece of code. For it to actually protect the machine, it has to wake up and phone home.
Right.
And according to the troubleshooting master checklist, this creates a massive friction point with the company's existing network security. The sensor actually has to fight its way out of the corporate network.
This is undoubtedly the most common point of failure in any enterprise deployment. You can have mathematically perfect tokens and flawless automation scripts, but if the local network infrastructure refuses to let the sensor communicate with the cloud, your entire deployment is useless.
So let's start with the baseline networking requirements. If you are listening to this on a corporate network, your company likely has massive firewalls restricting traffic. What exact path does the sensor need to take to talk to its commanders?
The network requirement is remarkably streamlined by design. The Falcon sensor communicates over TLS transport layer security on TCP port 443. And crucially, it is an entirely outbound, stateful connection.
Let's translate that for anyone who isn't deep into network engineering. TCP port 443 is the universal standard for encrypted web traffic.
Yes, exactly.
It's the exact same port your web browser uses right now to securely connect to your bank or your email provider.
Right. And CrowdStrike deliberately engineered the architecture to use port 443 because it's ubiquitous. If a corporate firewall blocked outbound traffic on port 443 by default, no employee could browse the internet or access any modern cloud application.
It's the one port that is almost guaranteed to be open for outbound traffic in any environment.
Yep.
I think of it like a secure mail chute in a corporate office building. The sensor on the laptop creates a sealed, encrypted envelope, drops it down the chute, and it slides all the way out of the building directly into the CrowdStrike cloud. You can confidently drop telemetry down that chute all day long.
I like that analogy.
But the most critical part of that architecture is the outbound-only nature. You do not need to open any inbound ports. Absolutely no one from the outside world needs to reach up into the building through that chute. The cloud never initiates an inbound connection to the laptop.
And that is a massive relief for corporate network security teams. In traditional networking, opening an inbound port on your firewall is terrifying. It's like leaving a ground floor window open in your corporate headquarters. It's an open invitation for threat actors on the internet to run automated port scanners, find the open window, and try to climb in.
But the sensor operates on a completely pull-based model.
Right. The sensor initiates the outbound connection, drops off its encrypted telemetry, asks the cloud, do you have any new policies or commands for me? Receives the response, and then gracefully closes the connection.
It sounds perfectly secure and highly efficient. So why did you say this is the most common point of failure? Where does the battle happen?
The battle happens when the company employs a technology called deep packet inspection, or DPI. The documentation highlights this as a major exam trap for administrators and a frequent cause of total deployment failure.
Okay, let's unpack deep packet inspection because this is a huge exam trap, like you said. DPI is a feature on advanced corporate firewalls, right? Its entire purpose is to inspect encrypted traffic, like the stuff flowing over port 443, to ensure employees aren't accidentally downloading malware hidden inside a secure HTTPS connection. DPI is fundamentally a security tool.
Yes, it is.
So why on earth would the Falcon sensor, which is also a security tool, have a massive problem with the corporate firewall?
To understand why these two security systems fight each other to the death, you have to understand the microscopic mechanics of exactly how deep packet inspection actually works.
Okay, lay out.
As we established, the traffic on port 443 is encrypted using TLS. A standard firewall can't see what's inside the data packets. It only sees the metadata that an encrypted envelope is traveling from your laptop to an IP address owned by CrowdStrike.
Right.
But a DPI firewall is designed to read the letter inside the envelope.
How does it do that if the connection uses strong cryptography?
By executing what is technically defined as a man-in-the-middle attack.
Wait, really?
I don't mean that metaphorically. The DPI firewall acts as a sanctioned corporate attacker. Let's walk through the TLS handshake.
Yeah.
Normally, when your laptop tries to securely connect to the CrowdStrike cloud, the cloud server sends down its public digital certificate.
Okay.
This certificate is cryptographically signed by a trusted root authority, essentially proving I am the real CrowdStrike server. Your computer verifies the math, and they establish a secure end-to-end encrypted tunnel.
But when a DPI firewall is in the middle...
The architecture breaks. When your laptop reaches out of the cloud, the local firewall intercepts the packet. The firewall puts the packet on hold, turns around, and establishes its own secure connection with the CrowdStrike cloud.
So the firewall is basically talking to the cloud on my behalf.
Yes. Then the firewall turns back to your laptop. It dynamically generates a fake digital certificate that says, I am the CrowdStrike cloud. It signs this fake certificate using the corporation's internal local certificate authority and presents it to your laptop.
So my laptop thinks it's establishing a secure, encrypted tunnel directly with the cloud in California, but it's actually establishing a tunnel with the DPI firewall appliance sitting in the server rack down the hall.
Exactly. Because the firewall now controls both sides of the encryption keys, it receives the secure data from the cloud, decrypts it, reads the raw contents to scan for malware, re-encrypts it using its spoofed certificate, and passes it down to your laptop.
It sits right in the middle, opening every single sealed envelope, reading the mail, and repackaging it before passing it along.
Yes.
I understand the mechanics of DPI now. It makes sense why a corporation wants to scan employee web traffic. But why does the Falcon sensor completely reject this? If the corporate firewall is just trying to be helpful and scan the telemetry, why does the sensor fail?
Because the sensor is fundamentally designed for zero trust. It does not know that the firewall is helpful. All the sensor knows is that it's attempting to transmit highly sensitive security telemetry to its command center, and some unknown entity in the middle is presenting a spoofed digital certificate in an attempt to intercept that data. The sensor uses an advanced defense mechanism called strict certificate pinning.
Certificate pinning? What exactly is it pinning?
It means the public cryptographic keys for the genuine CrowdStrike cloud are hard-coded or pinned directly into the compiled binaries of the sensor itself.
Oh.
The sensor doesn't rely on the Windows operating system's list of trusted certificates. It only trusts its own internal code. When it initiates that port 443 connection, it examines the certificate being presented by the server.
And if a local DPI firewall intercepts the traffic and presents a fake resigned certificate,
The sensor instantly detects the cryptographic mismatch.
the sensor looks at the math and says, wait a minute, you are claiming to be the CrowdStrike cloud, but I have the actual cryptographic signature of the cloud hard-coded into my DNA, and your math does not match. You are an imposter.
Precisely. And because its primary directive is to maintain the integrity of its data and prevent tampering by threat actors, the sensor assumes it's under an active, malicious man-in-the-middle attack. It assumes the corporate network has been completely compromised.
So what does it do?
Its programmed response is to immediately and forcefully refuse the connection. It drops the line.
And what does the IT administrator see when that happens?
They see a catastrophic deployment failure. In the local logs, this is documented as error 1232 total CloudCom failure.
Error 1232.
The deployment script ran flawlessly, the OS didn't reboot, the network cable is plugged in, and port 443 is technically open on the firewall. But absolutely zero data is flowing because the sensor refuses to speak to the imposter firewall.
This sounds like an unstoppable force meeting an immovable object. The firewall demands to intercept the traffic, and the sensor refuses to be intercepted. What is the solution? You obviously can't walk into the Chief Information Security Officer's office and demand they turn off their $1 million deep packet inspection firewall for the entire company.
You don't turn off the firewall globally, but you must configure an explicit surgical bypass.
Okay.
The administrator manuals dictate that network teams must log into their firewall or web proxy appliances and create a strict routing rule. The rule must state, any traffic destined for the specific IP addresses and URLs owned by the CrowdStrike cloud must completely bypass SSL interception and deep packet inspection.
You have to configure the firewall to let those specific envelopes pass through completely unopened?
Yes. Trusting the local network infrastructure, even your own highly expensive corporate firewall, breaks the fundamental guarantee of cloud resilience.
The center's ultimate allegiance is to the cloud tenant, not to the local IT department's network rules. If you interfere with that end-to-end encrypted line, the sensor intentionally goes dark to protect itself.
Exactly. The local network is always considered untrusted hostile territory.
Okay, so error 1232 is what happens when the network intercepts the traffic immediately upon installation. But let's look at a different operational scenario. Let's say the installation was perfect. The network team configured the DPI bypass correctly. The sensor has been happily chatting with the cloud, sending telemetry every few minutes for 6 months.
Everything is great.
Right. Then a senior executive takes their laptop and goes on a month-long sabbatical to a remote cabin in the woods with absolutely zero internet access. Or perhaps a desktop machine in a branch office gets unplugged during a renovation and sits in a dusty storage closet for a month.
Happens all the time.
The machine is completely isolated. It cannot reach the cloud. Does the sensor panic? Does it assume it's under attack and shut down the operating system?
No, it doesn't panic and it doesn't shut down the machine. It enters a highly specific, deliberately engineered fail-safe state called reduced functionality mode.
Reduced functionality mode. The manuals abbreviate this as RFM. What is the exact trigger mechanism for this state? If I am on a flight and I close my laptop, dropping the Wi-Fi connection, does it instantly drop into RFM?
No, momentary network drops are expected and handled seamlessly. The sensor is designed with a local cache. It will queue up its telemetry locally and wait for the connection to be restored.
So when does RFM actually kick in?
The documentation is incredibly rigid about the timeline. You must know exactly what causes RFM. A sensor drops into reduced functionality mode strictly when it loses communication with the CrowdStrike cloud for an extended, continuous period. Specifically, exactly 14 days.
14 days of total silence. Why 14 days? That seems like an arbitrary number. Why not 3 days or 30 days?
It's a meticulously calculated balance between operational reality and physical hardware limitations. 14 days is long enough to account for standard deviations in corporate life. An employee taking a 2-week vacation, a laptop being shipped across the country via ground freight, or a severe, prolonged site-wide IT outage.
You don't want the security architecture changing states just because someone went camping for a week.
Right. But beyond 14 days, you run into two massive problems. First, the sensor's understanding of the global threat landscape becomes dangerously outdated. But more importantly, you run into the physical limits of the host machine's memory and storage.
Let's expand on that. What does the sensor actually do that takes up so much space?
When a sensor is fully active, it is a voracious consumer of data. It is constantly hooking into the operating system's event tracing framework. It's recording every time a new process launches, every time a network connection is attempted, every time a file is modified, and every time a DNS query is made.
It generates a massive stream of microtelemetry.
Massive. Normally, it uploads this stream to the cloud in near real time, freeing up its local cache. But if it's isolated in that storage closet for weeks, it has nowhere to send the data.
Oh, I see the problem. If it generates, say, 10 megabytes of highly compressed telemetry a day, after 14 days, that's 140 megabytes. But if it keeps aggressively queuing that data for weeks or months, what happens?
It would eventually consume massive amounts of system RAM and CPU cycles, trying to manage an infinitely expanding queue of unsent data. The sensor would effectively become a resource parasite.
Oh, wow.
It could cause the machine to run incredibly slowly, or in the worst-case scenario, trigger an out-of-memory error that crashes the operating system.
So to prevent the security software from becoming a performance nightmare and destabilizing the user's computer, the sensor is programmed to deliberately scale back on day 15.
Exactly. It drastically reduces its resource consumption. It stops trying to aggressively trace and queue massive amounts of behavioral telemetry. It prioritizes the stability of the host machine above its own visibility functions.
It reminds me of a nuclear submarine going into ultra-low power mode when it realizes it's been cut off from command and cannot surface to communicate. It keeps the basic life support systems running, it keeps the reactor stable, but it turns off the massive active sonar arrays to conserve battery power and wait for rescue.
That is a very apt systemic analogy. In RFM, the sensor retains baseline foundational protections, like blocking known malware hashes, based on the very last set of policies it received before it went offline.
So it doesn't leave the machine completely defenseless.
No. But it is no longer operating at peak heuristic efficiency, and it is entirely incapable of sending visibility data back to the Security Operations Center. It is surviving, not thriving.
Now, I want to spend a minute here because the training manuals explicitly highlight that reduced functionality mode is surrounded by myths. It is apparently a massive trap on the administrator certification exams because people constantly misattribute the technical causes of RFM.
Yes, debunking the myths around RFM is critical for any IT professional. Let's be unequivocally clear about what does not cause a sensor to drop into reduced functionality mode.
Okay, myth number 1. My organization forgot to pay the invoice, our CrowdStrike license expired, and the cloud forced all my sensors into RFM to punish us until we pay the bill.
Completely false. RFM is not a licensing enforcement mechanism. If your organizational license expires, that is a console-level administrative issue. You might lose access to certain dashboards or features in the cloud interface, but the platform does not maliciously send a signal to tens of thousands of endpoints, forcing them into a degraded state.
So RFM is an endpoint-driven decision, not a cloud-driven punishment.
Right.
Okay, myth number 2. I was deploying the Sensor to an older machine, and I forgot to uninstall the legacy, clunky antivirus program first. The two security programs are currently fighting a brutal turf war for control of the Windows kernel, and that conflict caused the Falcon sensor to retreat into RFM to protect itself.
Again, false. Running two complex security agents simultaneously is a terrible idea.
Yeah.
The software conflict might cause severe performance degradation. The competing kernel hooks might cause a race condition that triggers a blue screen of death.
Yeah.
The legacy AV might even quarantine the Falcon installer files and block the deployment entirely. But a local software conflict does not trigger the specific engineered state of reduced functionality mode.
So, to reiterate this for everyone listening, because this is fundamental to understanding the architecture, RFM is purely, 100%, a symptom of prolonged cloud isolation. Exactly 14 days without establishing a successful TCP port 443 connection to the mothership. That is the sole operational trigger.
That is the primary defined trigger, yes.
Yeah.
The sensor analyzes its communication timestamps, hits the 14-day threshold, and scales down.
So if I am managing a massive fleet, how do I find these sleeping submarines? How do I know which laptops have been left in a desk drawer for a month so I can get them protected again?
The cloud platform makes hunting for them incredibly straightforward. The administrator logs into the host management dashboard, goes to the search query bar, and applies a highly specific filter syntax .status.rfma.
Status.rfma, nice and simple.
Yep. The cloud database will instantly filter through the hundreds of thousands of registered agent IDs and present a list of the exact machines that missed their 14-day check-in. The IT help desk can then physically track down those devices.
And then
The moment a technician opens the laptop and connects it to a functional network, the sensor will instantly establish a TLS connection to the cloud, download its updated prevention policies, flush its tiny cache, and automatically exit reduced functionality mode. No reboot required.
Okay, so let's summarize where we are. We've survived the deployment logistics using silent command lines. We bypassed the corporate DPI firewall trap by manipulating network routing rules. We understand how a sensor survives 14 days of network isolation by deliberately scaling back its resource footprint. We have built an incredibly resilient and visible deployment.
We have.
But according to the master troubleshooting guides, there is one final ultimate threat to this architecture. What if the enemy isn't a firewall? And the enemy isn't network latency? What if the enemy is a human being sitting directly at the keyboard?
You're talking about physical, authorized, local access to the machine. This is where the concept of zero trust is pushed to its absolute limits.
Yes. Let's explore the worst-case internal scenario. Let's say I am a highly skilled threat actor who has completely compromised a developer's laptop. Or frankly, let's say I'm just a rogue, disgruntled IT employee who is tired of the security software blocking my unauthorized crypto mining applications.
Unlikely, but possible.
I am logged into the machine as a local Windows administrator. I have root access. I am operating at Ring 3 with full privileges to manipulate Ring 0 components. I have the ultimate power over this specific operating system.
Right.
I can delete critical system files. I can modify the registry. I can format the hard drive.
You own the box.
I own the box. And I decide I want this invisible sensor gone. I open the Windows control panel. I navigate to add remove programs. I scroll down until I find the CrowdStrike Falcon sensor and I click the uninstall button. What happens mechanically?
If the cloud environment is configured correctly, absolutely nothing happens. Your attempt will be completely and utterly blocked by the sensor itself.
Blocked. But I just said, I am the local administrator, I own the access control lists, I have the highest level of privilege the operating system can possibly grant a user.
This is the ultimate expression of modern security architecture, and it fundamentally challenges how we view operating system hierarchy.
How so?
Within the Cloud Console, administrators can enable a setting called Uninstall and Maintenance Protection within the global sensor update policies. When this policy is pushed down to the sensor actively hooks into its own executable files, its registry keys, and its background services. And it explicitly denies modification access to everyone.
To everyone.
Yes, your local administrator rights mean absolutely nothing. You cannot remove the software through the control panel. You cannot run a corrupted .msi file to attempt a repair installation over the top of it.
What if I bypass the graphical interface? What if I open the Windows Services panel, find the background process running the sensor, right-click it, and forcefully tell the operating system to terminate the service?
The Windows kernel, entiskrnl.exe, will attempt to send a termination signal to the process. The sensor will intercept that signal, evaluate it, see that it lacks cryptographic authorization, and tell the Windows kernel, access denied.
Wow.
The sensor actively defends itself against the very operating system it resides in. Even if you have advanced privileges like cdebug privilege, the sensor's anti-tamper mechanisms will block the termination.
Going back to my original thought at the very beginning of this deep dive, it is exactly like having the physical master key to your own house, walking up to the front door and realizing the lock has been overridden by a satellite in orbit. Local physical authority is entirely, completely superseded by centralized cloud authority.
That is exactly what is happening mechanically. The sensor has essentially instructed the operating system, do not allow any human or process, regardless of their local privileges, to alter my state, stop my service, or remove my files unless they present a cryptographically verified token generated by the Cloud Command Center.
But wait, legitimate IT teams need to uninstall software sometimes. A laptop might have a failing hard drive and need to be retired, or a complex troubleshooting issue might require completely removing and reinstalling the security stack. If the local admin is entirely locked out, how is uninstallation actually achieved?
It requires a highly secure, out-of-band authorization workflow. A centrally authorized Falcon administrator, someone with high-level, multi-factor authenticated privileges in the Cloud Console, not just on the local machine, must log into the web interface.
Okay.
They navigate to the host management inventory, locate the specific machine that needs maintenance, and click a button to generate a unique maintenance token.
Another token. But in Section 1, we talked about installation tokens for creation. This is a token strictly for destruction.
Correct. And this token is vastly different. An installation token can be used thousands of times across an entire fleet. A maintenance token is uniquely seeded to one specific agent ID, and it's highly time-limited, often expiring in a matter of hours or days.
Okay, so once the cloud administrator generates that massive string of characters, they have to securely transmit it out of band via an encrypted chat or a phone call to the local technician sitting at the keyboard.
Right.
So the technician has this massive alphanumeric token. What do they do with it? They can't just paste it into the Add Remove Programs window because the UI doesn't accept passwords.
No. It requires a specific command line execution using the Windows installer framework. The technician must open an administrative command prompt and run mzxx.exe, explicitly passing the token as an installation property.
What's the exact execution string?
It looks like this: mzxx.exex pathdem package qn maintenance token.
Let's break that down like we did with the installation script. X tells the Windows installer to execute an uninstall routine. QN tells it to run quietly without user interface prompts. And then you pass the maintenance token parameter with that massive string. What happens under the hood when I hit enter?
The local sensor intercepts the uninstall command before it executes. It extracts the token you provided. If the machine is online, it might verify it against the cloud. But even if the machine is offline, the sensor uses an internal algorithmic hash check in HMAC to validate the math of the token against its own internal clock and agent ID.
And if the math checks out?
Only if the cryptography perfectly validates will the sensor disable its anti-tamper mechanisms and allow the operating system to remove its files. If you mistype a single character, or if the technician tries to use a token that expired 10 minutes ago, the sensor rejects the token and the uninstallation fails instantly.
It's a self-destruct sequence that requires two keys to be turned simultaneously. One key held by the technician on the machine, and one key authorized by the commander in the cloud. It ensures that no local compromise, no matter how deep or thorough, can result in the dismantling of the security perimeter without the central command structure explicitly authorizing it.
And that brings us full circle to the architecture of cloud-resilient defense. We have examined how a static customer ID requires dynamic installation tokens to prevent rogue deployments. We've explored the deep OS integration that allows for silent, zero-reboot deployments across 10,000 machines, while navigating Apple's strict MDM requirements.
We dissected the TLS handshake to understand why deep packet inspection firewalls cause error 1232 and why the network team must configure port 443 bypasses. We looked at the memory constraints that force a sensor into reduced functionality mode after 14 days of isolation. And finally, we just saw how the maintenance token strips away all local administrative power.
It is a remarkable piece of software engineering. But if we pull back from the command lines and the cryptographic hashes, I want to leave you with a philosophical point to consider regarding this entire architecture.
What point is that?
By deliberately stripping the local administrator of the power to control the security software, modern cybersecurity is making a very explicit, controversial statement, which is that human operators, even highly trained, fully authorized IT professionals sitting at the keyboard with administrative credentials, are the ultimate vulnerability in any system.
Right.
The paradigm of zero trust doesn't just apply to verifying network packets or checking file hashes or blocking malicious scripts. The architecture of the Falcon sensor proves that zero trust now applies directly to the person holding the mouse. The system fundamentally assumes that any local user, regardless of their credentials, could be compromised, coerced, or acting maliciously. The hardware no longer trusts the human.
So the provocative question we have to ask ourselves as we move further into this era of heavily managed endpoints is this. How much control over our own hardware are we willing to surrender to a centralized cloud authority in exchange for absolute security?
It's a tough balance.
If you cannot uninstall software from your own hard drive without asking a cloud server for permission, who really owns the computer sitting on your desk? It is a fascinating thing to mull over. The invisible guards aren't just watching the network for external threats. They are watching the very people operating the machines. Thank you for joining us on this deep dive into the architecture of enterprise security. We hope you walk away looking at the technology you interact with every day just a little bit differently, understanding the silent symphony of command lines, cryptographic tokens, and fail-safes silently guarding your digital life.